Greetings! Today we will learn about the so-called paging problem. Paging, it is a mathematical model of dealing with cache in computer memories. So the underlying thing is we have a, say, disk, computer disk, whatever, with say n memory pages, and it's just a number. Okay. Conveniently, these pages are labeled consecutively from 1 till n, and we have a cache memory. Cache. Yeah. So cache memory, say with k slots, and in each slot we can store a memory page. We can store a page. So basically, the cache configuration or a cache state is just a set, say C, which is a subset of these numbers 1 to n, such that the size of C is at most k. So we have k slots, we can fill each of them with some numbers, but no more numbers can be stored than k. Now that's the model. So basically some software or more softwares are just trying to access the memory on the disk, and in order to work with the contents of the disk we have to move them into the cache, and moving into the cache has some associated cost. But if the page which is just requested is already in the cache, then it's free because it don't have to be moved. And if there are already k pages in the cache, and the current request is for k plus 1, then we have to discard one page from the cache. That's free, but moving the new page into the cache is has a unit cost, the cost of 1. So we will want to minimize the cost, the total cost of page movements into the cache, also called cache misses. So the mathematical model is this, or a request sequence in online algorithms. We always have request sequences. Is some sigma. We usually denote these guys with sigmas, but not always. Sigma 2 and so on, and sigma, well, m. I don't want to use n because n indicates the number of memory pages, and m will, like Michael, will stand for the length of the input, which is of course not known in advance, I repeat. And each request is just a number, just an integer number between 1 and n. And then, well, action sequence. Well, just an action is some number tau between, well, it's a 0 and n, is just the ID of the page to be discarded in the current step before loading sigma I, the next one, into the step. Meaning, so after which the cache content of the cache becomes the cache content. It was C originally, but after this step it becomes C minus tau, so we just drop this guy plus the current request. So C is the empty set initially, the cache is initially empty. And in each step we have to maintain. Step we have to maintain that there are at most k pages stored in the cache. So basically this tau equals 0 means that there is no need to discard anything. So we now discard. Is needed. And I haven't told you anything about the cost yet, formally. So the cost is so it's free if the request is already in the cache, so 0 if sigma I is a member of C, well, Ci minus 1, so in the first time step. So basically we'll have this Ci minus 1 becomes Ci minus 1 blah blah blah, and this will be the content of the cache in the next step. So if the currently requested page is already in the cache and one otherwise. And that's it, we want to minimize the total cost. Now let's just see how it works on an example. So I'm just trying to, okay, so here we are. So example, in my examples usually k will be 3 and then won't contain that large numbers, but in practice, in the practice, well, it's more frequent to think about say a cache of 1 million pages and the memory of billions of pages, of course. So example, or at least 1000 versus millions. So at least for k equals 3 and n equals say 5. So I can get an input sequence of say accessing the first page first, then the third page, then the first again, and then say the second, why not, and then say the fourth, and then say the third again, and then say the fifth, and then say the fourth again, and then the first, and then the third again, and the second, like. So that's just a request sequence. So, and I have to serve this several ways. So and I can do this several ways. So, for example, and sequence is usually depicted as follows. Initially I have the empty cache. Then when the request comes for the page 1, I don't have to discard anything from the empty set, so I just output 0 as response and my current state becomes 1. So it's fine, 1 is served. And then a request comes for page 3, but still my cache has a size smaller than 3, so it makes no sense to discard this 1, which means I respond by 0. Yeah, okay, and right now both 1 and 3 are inside my cache. Then a request for 1 comes, and I'm lucky at this time because 1 is already stored in the cache, so I don't have to discard anything, I don't have to pay anything, and my cache still remains 1, 3. And then a request for 2 comes. Okay, but still, since the possible cache size is 3, I don't have to discard anything at this point, and my cache becomes 1, 2, 3. Okay, so this is a set. The order of the elements is not important, and I'm trying to keep this ordered just because I see it better this way. And then here, I just drew a line. Here, a request comes for page 4. So this is the point where I absolutely have to pay something, and I absolutely have to discard something as well. So for example, if I'm just discarding the page 3, why not? Then 3 is discarded, 1 and 2 remain in the cache, and I also move 4, the currently requested guy, into the cache. 1, 2, 4. And then a request comes for 3. Now this is where I probably made a wrong choice in the previous step, because this is exactly the element which I just discarded, so I will have to pay for this. And I'm just say throwing away the 4, why not? And then I will have the 1, 2, 3, because 4 is discarded and 3 is moved in. Fine. So we handle this 3. Now for 5 I have to discard something again, because 5 is not in the cache, but the cache is full. So I will just discard 1, say 2, 3 and 5. Okay, 5 is handled, and then I again get a request for 4, so well, I have to discard something. Say I will discard 2, why not? And it's 3, 4, 5. I'm just running an arbitrary example, have to formalize these things and have to compute the cost. I will get back to the cost in a minute. So say if I discard 5 at this point, when the request for page 1 arrives, I will end up with 1, 3, 4. Now it's fine because 3 is free, because it's in the cache, and then a request for 2 comes, so it's again 1, 3, 4, and then in the final step a request for 2 comes, and I will just discard page 4 and I will have 1, 2 and 3. Now, okay, so this input sequence is handled right now, and the cost. So for the cost, here I have to pay 1 because 1 is moved into the cache. Here I also have to pay because 3 is moved into the cache. Here I don't have to pay because 1 was already in the cache, but here I have to because 2 was not a member of the cache and 4 was not a member of the cache. Here I was not that lucky, so 3 was moved again, and 5 was moved again, and 4 was moved again, so I'm paying almost always something, so it's discarded again. But here this step was free because 3 was already in the cache, present in the cache, and here I also paid. So for this particular run, So this particular actions request cost is total 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 9 at this point. Now, okay, it's also known that, and we teach this fact for bachelors from the subject of operating systems, that the optimum cost is computed by the so-called LFD algorithm. So I'm just erasing this part and just run it on the very same input. So I'm just erasing this part. Maybe I will just try to remember that the runs cost was 9, so I'm not erasing that part, but I will try to compute the optimum cost for this particular instance, which is computed by, of course, an offline procedure, and we have to create some good enough approximation of the optimum using an online method. So the longest forward distance algorithm is an optimal one. I'm just sketching this here. Longest forward distance, longest forward or future if you wish. So the longest forward distance, okay, so the longest forward distance algorithm so if you have to discard something, well, then peek into the future. So this is not an online algorithm. And discard the page you don't need for the longest time. Yeah, so it's a greedy algorithm, but it's optimal. I won't prove this because it's not part of the online algorithms curriculum. For the longest time. So basically, this guy is optimal. It always computes an optimum solution, optimal solution. So back to our example, which was this 1, 2, 3, and so on. When we have to discard, so initially we are doing the same thing, so we are just loading the cache no matter what. So the LFD algorithm is not discarding pages unnecessarily, so it doesn't make any sense. So again, a request for 1 arrives, which means we don't have to discard, and then the fourth request was for page 2. That's fine. Okay, so we are here, 1, 2, 3. We are here at this line, because this line marks the end of the part where nearly all sane algorithms just push the newly requested stuff into the cache. So now 4 arrives, and then I check that 3 is accessed next time. Well, the next step. In the next step, 1 is accessed, say, this tongue ahead, but 2 is just accessed after 1 to 6 steps. So this 2 is requested, is not requested for the longest time from this time point, so I discard the 2. And then I end up with 1, 3, and 4. Okay. now do this again. You don't have to do this because 3 is requested, so you don't have to discard anything. So it's just 1, 3, 4 again. And then 5 is requested. So if 5 is requested, and here the cache content is 1, 3, and 4, then 4 is requested at this point, 1 is requested at this point, and 3 is requested at that point. So 3 is requested the latest among these guys. So we will discard 3 when we are processing the 5. So it will be 1, 4, and 5. Okay, so 4 is done. No, 5 is done. Okay, but then 4 is inside, so 4 is in the cache at this point. And then the 1 is also in the cache at this point, so I don't have to pay for these requests, nothing at all. And then 3 is requested. Okay, fine. I have to discard someone. Now this is the case where 1 is not requested anymore, 4 is not requested anymore, 5 is not requested anymore. So it can be treated as being requested after an infinite number of steps, and it doesn't really matter which one of these you choose. So as soon as you have someone who is not requested anymore, you can safely discard that guy. So let's just discard the 1, and then we will have 3, 4, 5, yeah, right? And finally there is a request for 2, and again I can discard anyone because no one is needed later on, so it's just 2, 4, 5. Okay, now let's do this. Let's compute this. So that is a cost of 1, 2, and this step again costs something, this again costs something, and that's fine. This has a cost, and these two also have a cost, so it's the optimal cost for this particular instance is 7. Okay, but even if you don't believe that LFD is an optimal algorithm, then well, we can probably agree on that this LFD actually computes some good solution, some valid solution. But this is not computed in an online manner. So, but there are online algorithms defined for this particular problem. So I just list now some online algorithms. So basically, what the difference between online algorithms is just who to discard. So if something is already in the cache, then you don't have to discard anything. That's fine. If the cache is not full, then you just load the just requested praise and don't discard anything. So if you have to discard, then there are strategies for doing that. For example, the FIFO algorithm, FIFO, which is just the same as the first in, first out, the FIFO is just maintains the cache as a queue, just as or data structure queue, and always discards the first time from the queue and pushes the new one to the end of the queue. So it's just discard the oldest page, say. Of course, you can think about what about LIFO, so it's LIFO. last in first out just maintain as a stack. Why not? So you just discard, in this case, the most recently loaded one. If you think about it, it doesn't make too much sense. And the most recently. But it's online. Now, something which can be seen as an improvement of FIFO is the LRU algorithm, which is a shorthand for least recently used. So the difference between FIFO and LRU is that FIFO always discards the page which was loaded into the cache least recently, and this guy discards the page which was last accessed least recently. Least recently accessed, so it just maintains a timestamp for each cache page. Least recently accessed. Now this sounds as it makes sense. And for example, there is also the least frequently used. In some actual real-time systems, it can make sense just to compute how many times a specific page had been accessed, because, well, there are objects usually in a software environment which are accessed frequently, and if they are accessed frequently for a short amount of time, then it's guaranteed that they will be also requested frequently in the future. So from this point of view, the life cycle of objects is usually like this. So this is the least frequently used. Is frequently used. You just have to count the number of accesses so far. Yeah, okay, so there can be two variants so far. The first would be to keep track of the whole history of all the disk pages. Now this is not really feasible, so we are just tracking this count to objects stored in the cache, but it won't make any difference, by the way, in the competitive ratio. So, and we drop this card. The least frequent one. Okay, so these are possible online algorithms for the problems. The FIFO, the LRU, the LIFO, and the LFO. These are all well, potential algorithms. Let's see them in action just to have some examples. I think it's not that bad to reuse this example, and I'm just trying to, well, I will erase this part. Okay, so this is the optimal algorithm. Now I know what will I do. This is the optimal algorithm, and here I'm drawing a line because that's the part where the cache is loaded. And then I will draw how the different algorithms behave differently in the remaining part of the input. So each algorithm starts with loading the cache, so I won't reiterate that part. And then, for example, the first one which we will check is the FIFO. So after 1, 2 and 3 and reading 4, it was, I think it was the 1 which was loaded first. Yeah, so 1 is the oldest page in this setting, and then 3 was loaded, and then 2 was loaded. So if I just read request for 4, then I will drop the 1 and I will end up with 2, 3 and 4. Now for this part, it's easier to me if I'm just maintain the order of these guys, just like as a FIFO container instead of a set. So it's 3, 2 and 4. And then the request for 3 is free. Okay, that's fine. So 3 is requested, which is good. And then comes a request for 5, so it's 3, 2 and 4, because nothing changed. And then comes the request for 5, and then I'm dropping 3 because this is the oldest one currently. And I'm just shifting left the other guys. Now 2 becomes the oldest one in the cache, the least recently loaded one in the cache, and 5 comes from the right side. And then comes, okay, so I'm here, so 3 is done, 5 is done, and then comes request for 4, which is fine because 4 is still in the cache, so it's free. So it's 2, 4 and 5. Okay, and then a request comes to 1, which is not in the cache anymore because we discarded it in the very first step. So I'm just dropping the oldest guy from the cache now, and it will become 4, 5 and 1. Cool. Okay, I'm just keeping track of, okay, so then 3 and then 2. Okay, I'm just trying to write this down. So 3, it will do something, and then 2 is the last request. Good. So 3 will just discard 4, so I will just have 5, 6 and 3 at this point. And then since 2 is not in the cache at this point, I will drop 5, which is just 1, 3 and 2. And in the next discarding step I will choose 1 and so on. Now the total cost of this run is, well, 3 for the initialization, so it was already 3 for this part, and this part. And then there were some costly maneuvers, so it was just, say, this guy had a cost. After loading the cache, exactly the non-zero responses have some cost. Yeah, 1, 2, 3, 4 and 5 maybe, right? 5 plus 3, so the cost of FIFO is 8. Well, it's larger than 7, but not that much, not by that much. Okay, now let's see what happens if we use, say, the LIFO. So at this point we just loaded well, the 1 first, then the 3 and the 2 at latest. So accessing 4 means that I will discard the 2, and then again I'm trying to keep this in an ordered manner. So 1 was the first one to be loaded, 3 was the second one to be loaded. I'm just dropping 2, which was the most recently loaded, and push 4 on place of that. Now then, the request for 3 comes. which is 3. Okay, so it's 1, 3, and 4. Then request for 5 comes. Well, in this case I'm dropping the 4 because that's the last element of the stack, so it's 1, 3, and 5. And then, well, request for 4 comes and I'm just dropping the 5. You can see it's not exactly a good algorithm. Okay, but 1 is free, so that's fine. 1, 3, and 4. Okay, so even Litho can get lucky because 3 is also in the cache. And then comes the last request for 2, and you just discard the 4. So it's 2. Now again, if you compute the cost of these guys, so we'll pay 1, 2, 3, and 4. 1, 2, 3, and 4. Now that's an interesting situation because in here Litho costs only 7, which is smaller than the previous 8. And then we can use the LFO, the least frequently used, or the LRU, which is the least recently used. I'll move with the LRU, and I will maintain timestamps along with these cache entries. So if 4 is accessed, then what happens? So originally it was the 1 which was accessed, then in the first time step, and then 3 was accessed in the second time step, and then 1 was accessed again, and 2 was accessed at the next time. So sorry for that. So basically 2 was the most recently used, then 1, then 3 was the least recently used among 1, 2, and 3. Now here I'm managing timestamps, so 1 was last time accessed in the third step, and 2 was accessed in the 4th step, and then 4 was accessed in the 5th step. Okay, so these superscripts are just timestamps indicating when was the last time a guy was accessed in the cache. So for example, right now 3 is accessed, 3 is not in the cache. This is the 6th time point, and I have to discard the oldest one, which was accessed the longest time before, and in this case this will be the 1, if I'm not. Yeah, so right now this is 1, 2, and 4, so these guys are in the cache. This guy was accessed in the 3rd step, this guy was accessed in the 4th, and this was accessed in the 5th. So indeed this 1 was at this point was the one which was the least recently used, and we know this because the timestamp of this guy is the smallest one. So we discard 1. The others will have the original timestamps, so it's 2, 4, and 3 was accessed just now, which is the 6th step, and then 4 retains its original timestamp, right? And then the next guy to access was 5. I'm copying this from this point. So 5 is not in the cache, so we have to discard 2 because right now that guy has the smallest timestamp. So we will have the 2, we will have discarded the 2, and we will have 3, 4 and 5, which was just arrived, and 5 will have a timestamp of 7 because that's the next possible timestamp, and the other 2 will retain their original timestamps. So right now 4 is the oldest one, but not anymore, because the next input is just a request for 4, so we don't have to discard anything, but we are updating the timestamp of the 4, because this is the access to the element which we keep track of. So in the 8th timestamp, 4 is accessed again, so it's safe for a couple of steps. And then a request comes to 1. A request comes to 1, and then we have to discard the 3 because that's the oldest, the least recently used one. So in the 9th timestamp we'll have several guys, for example 1, 4 and 5 in the cache. And then a request comes to 3, and for I will just discard the 5 because that guy has the oldest timestamp, and I'm just including the 3 in the cache with the original timestamps, and the and 3 will have updated timestamp. Cool. And then in the last step I will just discarding 4 because that's the oldest guy here. So it's 1, 2, 3, 2 entered in the 11th step, and 1 and 3 just maintain their positions. Now this is also not that good run, because the cost will be, say it was 3 for loading up the cache, and we have 1, 2, 3, 4, 7, 5, 6. So the least recently used algorithm will cost in total a 9 unit of cost for this. And then we can do the last one, the frequency counting, guys, so the least frequently used. Now in that case we are not maintaining timestamps, but we just count the number of accesses, and say here at this point 1 was already accessed 2 times and the other 2 guys were accessed 1 time respectively. So basically we had 1 accessed 2 times, 2 accessed 1 time, and 3 accessed 1 time. Okay, and then comes request to 4 in the original input, and I will drop 1 page with the smallest frequency count, so that would be either 2 or 3, and let's just drop the smallest one amongst these guys. So in this case is the 2, but still 1 was accessed twice, 3 was accessed once since it been loaded, and then 4 was accessed also once. And then after the 4, I think, after the 4, I think the next input was 3, which is fine because I'm just updating the number of accesses, so it's 3. And then 1 was accessed twice, and 3 was accessed twice, and 4 was accessed once since loading. I think I will just so it was 4, 3, okay, and then the next one is 5, right? Yeah, I'm just moving this upwards. So it's 5. Now I will discard the 4 because it was accessed only once. So I have the 1, I have the 3, and I have the 5 accessed only once. And then I have the 4. Okay, so this is again new at this point. So I'm just discarding the 5. So it's 1, which was already accessed twice, 3, which was already accessed twice, and now I have 5, which is already accessed once. Now recall this count is reset whenever I load the page, so it's just set to 1. I'm not keeping track of all the pages, all the numbers the pages have been accessed, because it would cost a tremendous amount of memory. So after loading the 4, okay, almost. I was just talking, it seems. So I just loaded the 4, right? And then, okay, 1 is arriving, which is great because it was already contained in the sequence, in the cache, but now it was accessed 3 times. The page 1 is just becoming more and more protected, and the same happens with page 3. So I'm just, yeah, okay, so it's request for 1 costs nothing, and the request for 3, I again don't have to discard anything, it costs nothing, it's free. But right now what happens is that it's almost sure that I have to drop the page 4 for the next request. But I think that's the last one. So 2, and for this I will have to drop 4, and I will have 1, 3, and 2, who is a fresh guy. Now again, that was the last part of the input, so I'm just computing the total cost. 1, 2, 3, 4, and basically that's it. So in this case, the least frequently used algorithm's cost is 7, which is optimal. Now there are these algorithms, right? The FIFO, the LIFO, the LRU, and the LFU. And right now it seems to be the case here for this particular input. LIFO and LFU produced an optimal solution, and then FIFO and LRU produced, well, suboptimal solutions for these particular inputs. Now in the next video or videos, it may happen that there will be more videos, we will just compute the competitive ratios of each of these algorithms. But till then, bye bye.